Hello, Mr. Claudia here. Today we're going to talk about proving trig identities. Now the idea of a proof is a really big thing in mathematics, but we don't see it a lot in high school math anymore. But going on in your mathematics studies, there are whole university courses and departments and math faculties dedicated to math proofs. So as an introduction, I want you to think back to probably in grade school when you had to talk about congruent triangles. This is where we were laying the groundwork for the idea of proof. How can I be sure that something is true and will always be true? So for example, prove that these two triangles are congruent. Prove that they're the same. Well, I mean, without doing anything too formal here, I know that the lengths are this length and this length are the same, but I need to make sure that the angles are the same too. Okay, well this angle I can figure out, right? This angle is 180 degrees minus 58 degrees minus 61. What's that give me? That gives me 61 degrees. Now I know that these two angles are the same because I know these two lengths are the same. So these are the same. So I know that each angle would be 180 degrees minus 58. So whatever the remaining, because all of them should add up to 180. So the two of them add up to 122. And then I take 122 and divide it in half because they're going to be identical. And that's going to give me 61 degrees. So I know that each of them is 61 degrees. So because this is 61, 61, 58, and then because these two sides are the same, I know that the two triangles are congruent. Because the three angles and one side length are the same, the triangles are proven to be congruent. So this is almost like a logic puzzle. How can I be sure? I mean, they don't necessarily look the same, but you have to do some thinking and kind of prove it. It's like kind of think of a Greek philosopher, arguing something with Archimedes, and they're proving certain axiom of math. That's kind of where this logic started. So a mathematical proof is a series of logical steps that show how one side of a mathematical statement is equivalent to the other side for all values of the variable. Now, like I said, there's a lot of different types of proofs, and there's much more than we can do in this one little section. But just to give you an idea, there's proofs by induction, proof by contradiction. What we're going to focus on is algebraic proofs. What you're going to try to do, and this is a whole manner of solving questions, it's different than anything you've seen before. You're going to separate an equation into two halves, the left-hand side and the right-hand side, and you're going to work at them separately. You're going to work until one side is equivalent to the other side. At that point, you can be sure that that you have proved the equation.
Note an identity symbol is three horizontal lines similar to an equal sign. It's used in place of an equal sign and indicates that the statement is an identity that is true for all values of the variables. An identity does not need to be solved by isolating for a variable. Instead, an identity needs to be proven by showing that the left side is equal to the right side. So let's start with a simple proof example. We want to show that 1/4 plus 1 over 12 equals 1 over 3. And now we want to prove its corresponding identity, 1 over m plus 1 plus 1 over m squared plus m is equivalent to 1 over m. So let's start with what we want to show. We want to show that 1 over 4 plus 1 over 12 equals 1 over 3. And since the left side has more things that we can manipulate, let's work with the left. So we say left side, and we write down 1 over 4 plus 1 over 12. We notice there's a greatest common denominator of 12, so we're going to multiply 1 over 4 by 3 on both the numerator and denominator to get 3 over 12 plus 1 over 12, which is equal to 4 over 12, and that simplifies down to 1 over 3. Then we write down the right side, and that is also 1 over 3. So since the left side is equal to the right side, we can write a conclusion statement. And we can also draw this black box. So what this black box means is QED, or in Latin, quod erat demonstratum, which means that the proof has been demonstrated. It means that it's been as shown. So it's just something that mathematicians usually use when they complete a proof. So we have a second proof of the corresponding identity. 1 over m plus 1 plus 1 over m squared plus m is equivalent to 1 over m. So like the previous question, we're going to start with what has more things to manipulate. So we start with the left side of 1 over m plus 1 over m squared plus m. We are going to get a greatest common, we're going to get the common denominator of m squared plus m times m plus 1. So I'm going to multiply the fraction on the left by m squared plus m and the fraction on the right by m plus 1. After that's been done, I'm going to collect like terms in the numerator, which will give us m squared plus 2m plus 1. And then I'm going to multiply out the denominator by FOIL. So we'll get m cubed plus m squared plus m squared plus m. We notice that we can also factor out a common value of m and collect like terms to get a denominator of m times m squared plus 2m plus 1, all in brackets. And that divides out to give us 1 over m. Then we consider the right side, which is also 1 over m. So we can write our conclusion statement that the left side is equal to the right side and that the proof has been shown.
In this section, you're going to be given some trig expression and you're going to have to prove the left side and the right side are true. Now, for questions requiring trig, I like to think that you have like a little toolbox, you know, of things that you can use to help you do this. Trig identities tend to be a stressful thing for students. They're not terrible in the IB program. They're really horrible in the regular grade 12 program. So you guys can consider yourself fortunate that you don't have to do them, do those really difficult questions. But imagine you have a toolbox that you're going to bring with you whenever you attack a trig identity. Inside that toolbox, you have all your known trig identities. So you have the Pythagorean identity. So sine squared plus cos squared is equal to 1. You have the tan identity. Tan x is equal to sine over cos. You have the double angle identity. So you have sine 2x is equal to 2 sine x cos x. And then you have the other double angle. So you have cos 2x. This one, you're probably going to forget. It's always, I always forget. It's 1 minus 2 sine x to sine squared x. Or what is it? 2 cos squared x minus 1, or cos squared x minus sine squared. These are all on your formula sheets, so there's no need to worry too much about them. You also have factoring is something you can do, and expanding. These are all strategies you can use to help you attack a trig identity proof. So let's do an example. Prove that sine squared theta is equal to half minus half cos 2 theta. Whoa, you can see that this is not going to be the nicest thing because look, I have 2 theta and theta. So I probably am going to have to use a double angle identity. Let's write this out in the correct method. We saw the word prove. That means I have to look at the left side and the right side separately. My left side is sine squared theta. My right side is half minus half cos 2 theta. Great. So now what I have to do is choose a side and manipulate it until I have the same thing on the right side and the left side. Let me attack the right side. There's not much going on over here. Makes more sense to attack this. I already see that I could common factor out a half, so I have 1 minus cos squared theta, or cos 2 theta. Now at this point, well, I guess I could go to my toolbox. Let me try replacing cos 2 theta. I could use another double angle identity. What does my spider sense tell me? Probably this one, because look, if I can replace the cos 2 theta with sine squared theta, then I'm getting a lot closer. So this is going to be half 1 minus, and then let me put that in brackets, 1 minus sine squared theta. Okay, and now, okay, I'm going to clean this up a little bit. So I have 1 minus 1 plus sine squared theta. And that gives me 1 minus, Did I forget something? Oh, I forgot the 2 here. Oh, how messy. Okay, and 1 minus 1 is 0, so this becomes half 2 sine squared theta. And 2 over 2 is 1, so I get sine squared theta. And there we go. Look at that. Left side is equal to right side. Write that. Or, again, what I like to put is the little square and QED. Great. So we have just proven that this statement is true for all angles, for all thetas, by looking at the left side and right side in isolation. Your homework is page 461, numbers 1 and 3 to 7. A lot of these aren't proof questions. I think there's only 1 or 2 proof questions in here. A lot of them are extensions of what we did yesterday, solving trig equations. So I didn't want to overload you yesterday. Let's overload you today. But especially yesterday, we were just getting used to the double angles, and now we're getting even more comfortable with them. That's your homework. Of course, the activity for today, the thing I want you to work through during class, is to prove these trig identities. So these are something I want you to work on your own, and then you can come back, unpause, and I'll go through them with you. Okay, so hopefully you finished doing these 7 questions on your own or with friends. Let's see how you did, and I'll go through kind of my answers here. So number 1, these first 2 are not trig, obviously, they're just algebraic. So I'm going to write out the left side, which is x minus 3 all squared plus 5, and the right side, which is x squared minus 6x. Ideally, I'm just going to use one side. I think I'm going to tackle this side first. So I'm going to FOIL this. So that's going to be, you want me to write that out? X minus 3 plus 5. So that's going to be x squared minus 3x plus 9 plus 5. Okay, and if I simplify this, this is x squared minus 6x plus 14, which is not the same as this. Actually, I made a typo when I entered this. It should be plus 14. This should be plus 14. And so then you see here, the left side is equal to right side. Or, you could do your QED thing. Okay, sorry about the mistake. Let's do number 2. So this one I have on the left side 1 over m, and the right side I have 1 over m plus 1 plus 1 over m squared plus m. Okay, well I'm going to tackle the right side here. Oh, you know what? I could make a common denominator, but what I'll do first is I'll factor the denominator of the second term here. I'll factor out an m, and that's going to leave me with m plus 1. This is good news for me. It makes my common denominator a little bit easier. I just need to multiply top and bottom here by m. So I end up with m plus 1 over m plus 1. There's lots of potential here. Now I can add these terms, so m plus 1 over m times m plus 1. The m plus 1 cancels out, so I'm left with 1 over m, which is great, right? That's a great proof. Okay, let's keep going. Number 3. This one, the left side is tan 2x minus 2 tan 2x sine squared x. Oof, that looks terrible. And the right side is sine 2x. Okay, well, let me leave the right side. I find it's easier to kind of try to condense some of these things on the left side. Okay, so first of all, when you see the tan 2x, I mean, that is technically in brackets, right? Or, well, you don't have to write this out, but that's the argument of the tan function. So actually what I see here is tan. I have 2 terms, and they both contain tan. So remember my toolkit of options, one of them is factoring, and I'm going to do that first. Let me factor out the tan 2x. What's left when I do that? Well, tan 2x goes into itself once, and then I'm left with 2 sine squared x here. Again, I'm trying to get to sine 2x. Okay, well, essentially need to, like the first thing I can do is I need to get rid of this x because this is a 2x, right? So what can I do? Is there a way of converting this angle into a double angle? Well, if you remember, actually that looks a lot like the double angle formula for cos 2x, right? 1 minus 2 sine squared x, that equals cos 2x. So there it is right there. So let me just see where this goes. And sometimes you'll find with these questions, you're going to try a lot of things. You might go in circles and then loop around again, and eventually it'll work out. So let me just follow this idea, this hunch I have. Still, it's not quite there, but the good news is now I have everything is in terms of 2x. Let me try getting rid of this tan. Classic way of getting rid of the tan is with that that second trig identity we know. Tan 2x is equal to sine 2x over cos 2x times cos 2x. And there it is. These two cancel out, fraction, and I'm left with sine 2x. Great news. Let's see if we can squeeze another one onto this page. Question 4. This one is, let's see it, left side, cos x tan cubed x, and my right side is sine x tan squared x. Okay, for this question, what am I going to do? Well, here I have tan. So if only I could get rid of or factor out one of these tans, I would, if I could remove one of these tans and I could leave tan squared, let's see what happens if I do that. So if I had cos x, and then I had tan x, and then tan squared x. And then I can change that tan x into sine x over cos x times tan squared x. And there we go, it happens again. I have cos and I have cos cancel out, so I'm left with sine x tan squared x. Great. You might think, like, is there more to this? Well, you are fortunate in the IB program, or IBSL at least. There are really only these 4 identities you have to work with, right? Your regular grade 12 program in Ontario curriculum, you would have you'd have to worry about the reciprocal trig functions. You'd have a lot more kind of, identities. You have a lot more trig identities to worry about. But it's pretty streamlined in IB, and there's really only a few options. These two are almost pretty intuitive. You've seen them so many times. And these, well, there is a connection here between the double angle and the single angle. So that's a big clue that you have to use them. Okay, let's continue to question 5. So this is section 10.7. We're at page 3 now. So when I'm on question 5. Okay, so this one is left side, sine x plus cos x squared. And I have my right side, which is 1 plus sine 2x. Oh, sorry, there we go. So in this question, I've got a bit of a problem here because I see that my I see that this is a double angle and these are single angles. Now remember I have that single angle or the double angle formula with cos squared and sine squared, but yeah, they're being subtracted, so that, and they're squared, so that doesn't work here. Remember though, one of my tools in my toolbox is to actually expand, and this can be foiled, right? This, if you want to write out that step, looks like that. So if I FOIL it, I get sine times sine, which is sine squared x. Then I have sine times cos twice. And then I have cos times cos, so that's plus cos squared x. I'm still not really seeing it. Oh, although, what if I rewrote it like this? Sine squared x plus cos squared x. Actually, both those things look familiar. Sine squared x plus cos squared x. Well, that is my Pythagorean identity right there. That's just equal to 1. And 2 sine cos, well, that is my double angle formula. So I end up with 1 plus sine 2x. Left side equals right side. Great news. Let's go on to question 6. This one is sine squared. Left side is sine squared theta cos to the 4 theta. Oops. And then over here I have my right side is equal to cos squared theta plus sine to the 4 theta. Now remember, it's okay if you work on both the left side and right side until they are the same. It's just cleaner if you can do all the work on one side. Okay, so with this question, let me tackle this one. I guess I'll start with the left side. So I don't like the cos to the 4 because over here there's a cos to the 2. So why don't I split that up? So I'd have, did I write this question out wrong? I did. It's sine squared plus cos squared. Okay, well let me rewrite this. Plus cos squared theta times cos squared theta. So now at least I have a cos squared theta there. There's no double angles really involved here. So what other options do I have, right? Like if I'm not dealing with double angles, I really only have I don't want to introduce any tans, so I really only have this, my Pythagorean identity. Now, cos squared I could actually write as 1 minus sine squared. So let me do that. Let me see where that takes me. So I have sine squared theta plus, and let's replace cos squared theta with 1 minus sine squared theta. And then I guess the same thing here, 1 minus sine squared theta. Maybe I'll just make a note so it's clear where that came from. That's sine squared theta plus cos squared theta is equal to 1. So then I have 1 minus sine squared theta is equal to cos squared theta. So that's where that came from. Okay, now, well, I guess I'll just follow the rabbit hole here and FOIL this or expand it. So I have sine squared theta plus, and then I end up with, should I do this in a bracket? 1 times 1, which is 1. Negative sine squared minus, so minus 2 sine squared theta. And then this becomes positive sine to the 4 theta. Okay, and now I have sine squared theta minus 2 sine squared theta plus 1. So that gives me, 1 minus sine squared theta plus sine to the 4 theta. 1 minus sine squared theta we've already established is cos squared theta plus sine 4 theta. So that's QED. Thus is proven. And you might have done it a different way, right? This is just kind of when I attacked this question, this is the process I kind of went through, but you might have done it in a shorter number of steps. Finally, let's do number 7. This question is left side. Tan squared beta plus cos squared beta plus sine squared beta. And the left side, or the right side, sorry, is 1 over cos squared beta. Okay, for this last question, what am I going to attack here? Again, I find it easier to kind of bring these things together. And, okay, well, let's see. Tan squared theta, this has no tans in it. So let me get rid of the tans. Tan is sine squared beta over cos squared beta. This is plus cos squared beta plus sine squared beta. Okay, now this final answer is 1 fraction. Here I have 3 fractions. This is over 1, this is over 1. Why don't I make this a common denominator so I can add them? So I'm going to multiply the bottoms by cos squared beta. So I have sine squared beta for cos squared beta. This one is going to become cos to the power 4 beta over cos squared beta. This one is going to become sine squared beta cos squared beta over cos squared beta. Now I can add all these things. Well, I guess it's kind of clear I'm adding them all here. So I have sine squared beta plus cos to the 4 beta plus sine squared beta cos squared beta over cos squared beta. This is tricky because now it's actually gotten a lot worse. What am I trying to do? Well, actually the denominator looks good. It's cos squared beta. So now I just have to add all these things up. Well, there are a few different ways of solving this. I mean, essentially what I need is for the sine squareds to go away and the cos squareds to go away. You can do this a multitude number of ways. I'm going to actually look at the last term. I'm going to replace the sine squared with 1 minus cos squared. Again, that's just the Pythagorean theorem rewritten, just like we did up in the earlier question. Again, you might do this a different way. Oh, sorry, over this denominator. There are a lot, but you're going to end up with kind of the same result. That's cos to the 4 beta over cos squared beta. So what do we see here? These things subtract out. I end up with sine squared. Oops, can't see anything. Oh, those cancel out. The cos to the 4b beta minus cos to the 4 beta. So now I have sine squared beta plus cos squared beta over cos squared beta, and that is going to be Pythagorean theorem 1 over cos squared beta. I ran out of space there. It's not the nicest ending, but I did get left side is equal to right side. So there you have it, a whole bunch of proofs. Your solutions might be slightly different as long as you arrived at the same kind of conclusion. Good luck. There's that homework I gave you, right? Remember, there's some more practice for you to do on your own. A lot of it is similar to our equations lesson that we did a few days ago. Good luck with that, and we'll see you next time.